Okay, we're going to look at a problem now that highlights two particular things. Number one, the difference from position and displacement, as well as how to use quadratic formula in order to solve a problem. Let's begin by looking at the problem. We have a clown who's tired of his career, who throws his pack of ridiculous things, such as an oversized shoes, red nose, collection of whipped cream pies, whatever. Point is, he throws them into the air in disgust at 10 meters per second. He throws it from a height of 1.2 meters. Which makes sense because he's probably not going to be, having this stuff directly on the ground. How high does it go? How long before it hits the ground? We'll begin with the first question. The first question particularly highlights position versus displacement. Not that we're graphing them here, just what's the difference between the two of them. What you've been given right here is not a displacement, but in fact a position. So when you write out your situation here, let's begin by giving, it's this crazy fuzzy hair. Looks like he's wearing, spikes or whatever, but he's got a red nose right there. That's not bad. It's almost like perspective, like we're looking down on him. Anyway, so he's got his collection of stuff, so let's go with his collection of stuff that he's going to throw into the air at 10 meters per second. As typically is the case, I'm going to set up as positive in this particular problem. Now notice that he is starting this at 1.2 meters above the ground. This is not how far he threw it above that point. That is right here. So this is its initial position or height, and this is how far it's going to go during this time. When we set up this equation with our 5 variables, this displacement, therefore, will not give us the answer of what the height is. What it will tell us is how far it's gone from its original position. Given that the initial speed is 10 meters per second, the acceleration is 9.81 meters per second squared, and of course if it's going to stop at its max height, the final velocity should be 0. We can use this information to fairly easily find out what displacement is, but that is not the total height, because of course we'll just have to add this 1.2 in the very end. So I'm going to solve for displacement right now very simply by using the equation vf squared equals vi squared plus 2a delta x. Vf, of course, will cancel because it's 0. Subtract the vi squared over, divide by 2a, that's equal to delta x. And there we go. We have our equation here. Very simple. Again, we'll comment that the negative here is not going to be squared, but anything inside would be. So 10 meters per second, which will be squared. There's a negative out in front of that, divided by 2 times negative 9.81 meters per second squared. And the calculator tells me that the answer is 5.10 meters. This is how much displacement goes on top of what it was going to be right here. So the answer to height is not 5.1, but instead my initial position plus my change in position, which will give me my position final. That's 1.2 meters plus 5.10 meters, which tells me that my final total height is 6.3 meters. This highlights the particular difference between position and displacement. Okay, now I want to look at this problem for the second part. How long before it hits the ground? Now, with all physics problems, there's a couple ways to do this. I could have actually just figured out in the last part how much time it took to go up, and then I could have figured out how much time it takes to go down on the other side. But I want to use this opportunity to show you how you can use the quadratic formula to solve this problem. I've gone back and I've reset this, so I didn't put the arrow up, and of course I'm not putting velocity final as 0, because that's not what I'm looking at anymore. Before I had my initial position here and my final position up here in order to accommodate what we needed. What I'm going to do now is I'm going to make my initial position here and my final position right here. So I'm going to account for that in here. My initial velocity is still 10 because I'm still starting at the same spot. My acceleration is still negative 9.81 meters per second squared, but my velocity final is definitely not 0 anymore because it's changed all the way up. It'll go back to -10 at this spot due to symmetry of motion, and it'll probably be above -10 when it hits the ground. Not probably, it definitely will. So I don't know what the velocity final is. I also don't know what the time is. But what I do know is I know the displacement. I know that the total change in position during this time is -1.2 meters, because it's 1.2 meters in the negative direction from where it began. -1.2 meters. Now I need to find time. So I pull out the equation, displacement equals velocity initial times time plus 1/2 a delta t squared. If you get this equation out and you see that, of course, that none of these things are going to cancel, then you know you're going to have to use quadratic. So the simple way to do this is to get this in the form of a quadratic equation. The form of a quadratic equation is 0 is equal to ax squared plus bx plus c, where x is our variable. In this case, t is our variable, so we're going to try to get it to look exactly like this. Before I do that, I'm going to put numbers in, which is not common for me, but I want to make sure that you can see the numbers move as you're used to. The delta x in this case is -1.2 meters. Velocity initial is that 10 meters per second we had earlier, plus the 1/2 times -9.81 meters per second squared times delta t squared. Before I do anything, you'll notice I need to get this set equal to 0. While I'm doing that, I'm also going to take the time to make sure that it's in the proper order. So I'm going to get my x squared or my t squared first. While I do that, I'm also going to simplify here. So I set my equal sign in the same spot so I don't lose track of things. This is going to be -4.905 meters per second squared to the 1/2 delta t squared. Then I'll have my x term, which is my t term, plus 10 meters per second times delta t. And finally, you'll notice that in order to get this equal to 0, this has to be added over here on this side, plus 1.2 meters. Now this is in the proper form of the quadratic. Whatever constant is next to my t squared, that's going to be my a. Whatever constant is next to my t to the first power, like my x to the first power, that'll be my b. And whatever constant does not have a variable next to it, that will be my c. And I plug it into this equation right here. -b plus or minus the square root b squared minus 4 ac all over 2a. If I plug this in appropriately, I should be able to get both answers. Okay? So I have -b, which is -10 meters per second, plus or minus the square root of b squared, that's 10 meters per second squared, minus 4 times a, which is -4.905 meters per second squared, times c, a positive 1.2 meters. If I use my units in here, to use unit analysis, you'll notice that meters will be squared, seconds will be squared, so this term over here will be, it's kind of hard to see with my terrible writing, this whole term will be meters squared over second squared, and you'll notice that this term will be as well. When you add or subtract, everything in here will be meters over second squared, and the square root will take us to meters over seconds. And that will all be divided by 2 times -4.905 meters per second squared. Okay. The calculator tells me that the square root portion over here is 11.12. Again, as we pointed out a moment ago, the units on that are going to be meters per second. And so now, in order to get my two answers, I'm going to take plus and I'm going to take minus. Okay, when I add, my first answer to t is -0.11 seconds. When I subtract, I actually get a positive 2.15 seconds, which is my actual answer in this case. Now you might ask, why is there a negative answer in the beginning? Why is there two answers at all? There should only be one time in which the displacement is -1.2. The answer to that very simply is that the math doesn't know exactly what happened, while you're doing physics. So what the math does is it says that if this trend were to continue in this particular way backwards, then it would have been at this spot negative 0.11 seconds before. Or the negative implies here that this would have happened before we started measuring time. So if ever you see a negative on your time under the square root, it's very easy to know if that is not the correct answer, and so that your other one is definitely the correct answer. And that's how you can use quadratic in order to solve these problems.